Good evening, all. Welcome to week 6 of the session of Engineering Thermodynamics. So this week we'll be discussing on most all of the problems we'll be dealing with the steam tables. So we'll learn how to use steam tables to solve some of these problems. We'll wait for a couple of more minutes to let people join, and then we'll get started around 5 to. Okay, we'll get started. So as you join, you can go through the problem later on the recorded session as well. The first question here is there is steam at 7 bar pressure and a dryness fraction of 0.9, which expands in a cylinder behind piston isothermally and reversibly to a final pressure of 1.5 bar. Calculate the change in internal energy and change in enthalpy per kilogram of steam. The heat supplied to the process is found to be say 400 kilojoule, and then calculate the work done for that steam for this process per kg of steam. So basically we were asked two questions. The first one is to find the change in internal energy, and next part asks you to find the work done. Q is already given to us. Heat supplied, it says, since it says it is heat supplied, so this will be a positive value. So if you can calculate delta U, then work is straightforward. How do I calculate delta U? I just need to know the initial and final states, and it doesn't depend on any process. It doesn't matter whether it is okay. So how do I write it? The initial state is given. P1 is given as 7 bar, and initial vapor fraction is also provided. From this, it is moving to a pressure of. Is any other information provided? So just to reiterate some of these points here. So until now we have been discussing problems on, even in the last week we were discussing problems on related to ideal gas. So in case of an ideal gas, when you have an isothermal reversible process, like the one that is described here in an isothermal process, in ideal gas your U is only a function of temperature. So for an ideal gas you have delta U is CVDT, and your CV is not a function of temperature. So what happens in an isothermal process is delta U equals to 0. But this is only for an ideal gas. Now when we are discussing about steam, what happens is even though it is an isothermal process, there is some internal energy that is, as you see that when it expands, some part of the liquid gets converted into vapor, because of which there will be a change in the internal energy. So in order to account for those things, we have tabulated, we have some steam tables that we can use, or you can nowadays you can also directly look up the values from some of the algorithms or modules that are available online. For this particular course, we will restrict ourselves to steam tables, looking at the steam tables and getting these values. So for one thing, we know that it is an isothermal process. So T2 equals to T1. Since it is having a dryness fraction of 0.9, which means if you consider the vapor dome, so if you consider a PV plot, so you are somewhere at a pressure of 7 bar, and then your vapor fraction is 0.9, so you're close to your vapor dome. So this is somewhere your initial state. Now you are expanding isothermally. So what would happen? Your isothermal curve will be something like this. So now when you expand isothermally, you move up until the vapor dome, and once you reach the vapor dome, what happens after that is we will see what happens in the superheated region. First, we'll evaluate the properties at this particular point. How will I calculate T1? T1 is basically the saturated temperature at 7 bar pressure. For that, I can look up the steam tables. So if I switch to steam tables, like as we discussed before, so we have two different kinds of tables here. So one is tabulated along temperature, but in this case, I want to look up for a pressure, so I look up a different table. So this is a pressure table. This is what we will be looking up now. In the pressure table, this is in bar. Just make sure of the units. We need to look up a value for a 7 bar pressure. If you look up at 7 bar pressure, the temperature is 165 Celsius. Similarly, this is my VF, UG, or the specific volume for the liquid phase for the vapor one, and this is the UF and UG. So if you just take a note of these values, so we have temperature to be around 165. We got T1 to be 165 Celsius. Now in order to calculate the U1, we need to know the vapor fraction. So we know the vapor fraction is 0.9, so we require both the liquid phase U and the vapor phase also. So if UF is the liquid phase one, so we have 1 minus x times UF plus x times UG, where these two values you can take from the steam tables. So the value at 7 bar pressure, we have a UF of 696.44 and UG of around 2572.5. These are the values we'll be looking at. If you just take down those values, and we already know the value of x to be 0.9, so if you substitute that, you will get U1 as now. How do I determine the second stage? I know my pressure as 1.5 bar and temperature T2 equals to T1 as equal to 165 Celsius. Now with these values known, how can I calculate my next U2. So I know pressure and temperature. So I can directly look up the table for 1.5 bar. If you look up the value at 1.5 bar, at 1.5 bar, we have a temperature of around 114, 111.4, but the temperature we require is 165 Celsius, which means we are in a region different from, we are in the super saturated region. So we should look the superheated tables. So this is my saturation point. So here the temperature is so if this is my isothermal line that would go along this, and then so I'm at initial stasis 1. And what happens if you're moving along the line? You'll be moving along this line. So, but your temperature is constant. So this temperature is around 165 Celsius. You will end up at a new point where it is given that the final stage is at 1.5 bar. So this is your final state 2. I need to find the value of u at this particular stage. So how do you go about that? Like we discussed in uh, a couple of weeks back, you can calculate this directly from the superheated steam tables. Alternatively, you can also calculate it using assuming that the steam follows the ideal gas law in this region, so that you can use ideal gas law and directly calculate the internal energy from there. How do you go about doing that? Is basically you calculate CV. So if you know the value of u at this particular point, so let's call this point as 2g. So you know that u2 minus, yeah, hi. So I was just going through a couple of problems on dealing with steam tables. So you can go through the problem and try it out yourself. While I was also like in the middle of the problem, so I'll just complete it. So you can also try it yourself. And if you have any doubts, we can discuss. Yeah, so I was saying, so now that we know that the second stays in the superheated region, so we need to find the value of U2 at this particular point. So we look up the superheated steam tables. If you look up the superheated steam tables, you have the values of in terms of the pressure. So the final pressure is 1.5 bar. So you directly look up the value at 1.5 bar, and then the saturated temperature is 165 Celsius. So which is not directly available, but then other values are available. So you need to interpolate it at 165 Celsius. The value that we are requiring is internal energy. So you can do a linear interpolation to find the value of U here. Just to be, just take one more step, it will be clear. You can use this value directly. So we have the values of U2 and U1 directly here. We can calculate delta U from there. We already used the first law, so from there we can calculate W directly. Okay, the 2 points that I would like to draw your attention here is one, delta U is not equal to 0. If we have a phase change process. Okay, are there any queries? Okay, I guess there are no questions. Or if there are any questions? Okay, we'll move on to the next problem. All of these are very straightforward problems if you can look up the steam tables. So for example, like the second problem is you have certain 1 kilogram of steam at 100 bar pressure and this is 375 Celsius, and it expands reversibly in a perfectly thermally insulated cylinder behind a piston until the final pressure is 38 bar and the steam is then saturated. Calculate the work done by the steam. So the first thing, any of these problems, you start with your first law. So you have Q equals to delta U plus W. Here it is mentioned it is a perfectly thermally insulated cylinder. So your Q is 0. So now you have delta U and W. You are required to find W. So W is minus delta U. That is U1 minus U2. So if you can calculate U1 and U2, then the problem is solved. So what do I know about U1? Initial state. Initial pressure is given. Initial temperature is given. Final pressure is given. Do I know final temperature? It is given that the steam is saturated. So in the saturated vapor state, I can use the saturated temperature to get the value of T2. So I'll use the saturated temperature at this point. So how do I calculate the value here? So at 100 bar and 375 Celsius, so if you look up the steam table, if you look at 100 bar, the temperature is around 311.1 Celsius. But the temperature that we have is 375 Celsius. So which means if you look at from the Euler diagram, so this is your PV plot. You are at 100 bar pressure. And this is your temperature curve, isothermal line. This is my 375 Celsius line. And this is my 311.1 Celsius, which means you are in the superheated region. So you have to look up the superheated steam tables. So again, we go to the superheated steam tables, check the value at 100 bar pressure. This is a 100 bar table, and you need to look up a value for 375 Celsius. The values that we have here are 360 and 400. So you can do a weighted average. of the property that I was looking here is for you need to calculate internal energy. So you just calculate internal energy values. So these are the values that are given. So how do you get the final value at 375? So you have it 360 and 400. At 360, the value is just linear weightage. So what is the value of U1? Now, how do I calculate U2? We know it is in the saturated region, which means all I need to do is calculate the value of Ug, that is the value for the vapor phase at 38 bar pressure. So again, you look up the steam tables. You look up the temperature or the pressure. Like the pressure is given as 38 bar, so you look up the value from the pressure table. At 38 bar, so here we have 35 and 40. So again, we have to do a linear combination. So this is the UF values and these are the UG values. We know that it is in the saturated vapor region. So these are the values these are the values I should be using. So we know at 35. Since the values are close enough, you can directly take the close to. We have the values of U1 and U2, so you can directly calculate the work done from there. The mass is also given as 1 kilogram, so I'm just ignoring that. So you can just multiply with 1. So your work done will be U1 minus U2. I'm just ignoring the mass term for now. So you have kilojoule. Okay, my screen is not visible. So I hadn't noticed your message. Yeah, sorry, I think my screen is not visible up until now. So let me know if you can see the screen now. Yeah, I hope the screen is visible now. We'll move on to the next problem. In a steam engine, the steam at the beginning of the expansion process is at certain pressure and a dryness fraction of 0.95. And expansion follows a particular law. It's a polytropic process. So we have PV to the power n equal to constant. And this expansion is allowed till the final pressure reaches 0.34 bar. Calculate the work done per kilogram of steam during the expansion and the heat flow per kilogram of steam to or from the cylinder walls during the expansion. Again, you use the first law. The only difference from the previous problems here is in all the previous problems, the work done we were able to calculate like the processes were known. in this you have a polytropic process, so you just use the formula for the polytropic process. So initial pressure and dryness fraction is given, and we know the process. Okay, so how do you calculate the work done? So Q is asked, so Q is W plus delta U. I'll just write U2 minus U1, and W for a polytropic process is given by V2 V2 minus V1 V1 by 1 minus N. In this particular case, N is 1.1. So in order to calculate Q and W, I need to know, so out of all these parameters, I need to know V2. V2 is already known, V2 is something that I do not know, V1 is something that I do not know, U1 and U2. These four are the quantities that I need to determine, and I will be able to solve the problem directly. So what is V1? You know the initial pressure and initial dryness fraction. So you can calculate V1. We look up the steam table and then take the values directly from there. It is at 7 bar pressure. So at 7 bar pressure, we need two properties. We need V1 as well as U1. So V1 is 1 minus, and just note that the value over here is to be multiplied with 10 power minus 3. So you can see that here when you are using this value. And similarly U1, this and this. Now that I have V1 and U1, so I have V1 and U1. I need to calculate V2 and U2. How do I calculate V2? I use the process equation. So I use this equation M1, so I can calculate V2 as P1 by P2 to the power 1 by 1.1 times V1. So I have my final volume. So now how do I calculate U here? We know the final pressure and we know the final volume. So we know P2, we know V2. So how do I calculate U from there? If you look up the steam table at 3.4, 0.34 bar, we do not have 0.34 bar directly here. We have a zero point 0.3 bar and zero point 0.4 bar. So at 0.34 bar, we need to determine the value of U. And the only things that we know here are the P and V. So if you look at it from a PV plot, this is my PV plot. I know the values of P and V and I need to determine the corresponding U. So I know my pressure. All I need to do is map with the corresponding value of V. So how do I do that? So we have three different values. So we have at 0.3 bar, so basically this is a two-step process. So let me just write it down. How do I interpolate it here? You have a table at P equal to zero point 0.3 and you have something at zero point 0.4 bar. If this is my pressure, you can calculate Vf, Vg, Uf and Ug. So from this you will calculate the value, you use a linear interpolation and then determine the value of Vf, Vg, Uf, Ug at 0.3 bar. This is for the first step. The next step is once you do this, you know the actual value of specific volume here. So when you use the actual volume of V2, from there you get the vapor fraction. And once you get the vapor fraction, you use these values of Uf and Ug and from there you calculate the value of U. I hope this is clear. You can just do the calculation yourself while I'll just populate the data here. So if you see at 0.3 bar, you have Vf of, I'm just ignoring the 10 power minus 3 because that will go in the final equation. And you know the value of Uf and Ug as well. So I'm leaving down the math for you so we can do the linear combination here and tell me the value of Vf at 0.38 bar. Similarly, we can calculate Vg. With these values, and you also already know the value of, you just populate the values here. So I calculate the values of Vf, Vg here. Vf, and I'll just copy paste the values. Once I have these values, how do I calculate V2? V2 is already known to me. So all I have to do is just find the vapor fraction. So how is the vapor fraction defined? V2 minus Vf by Vg minus Vf. So you can also observe that V2 here is actually less than Vg, so that it is within the dome. And just to reiterate that here we have 10 raised to the minus 3. Once I calculate the vapor fraction, I can calculate Q2 directly as 1 minus x2 times Uf plus x2 times Ug. I have P1, V1, P2, V2, and U1 and U2. So I have all the variables that I require. So our work done is straightforward. So we just substitute this in the formula. So we have P2, V2 minus P1, V1 by 1 minus n, where I'm just converting it to appropriate units. Just multiply with 100. We'll do it in the last. That is just to convert it to kilojoule per kg. And we have the final volume to be 4.05526. And I already have U1 and U2 with me, so I can directly calculate the Q. I'm not sure about the number, so you can also quickly go through the calculations and then let me know if there are any mistakes that I have made in the calculation. But is the process clear? The only thing that we have done extra here from the last problem is now that we have to do two interpolations. The first interpolation is because you have a value of pressure, like you need to determine the properties at a pressure that is not provided directly in the steam table. Second, we up until now we have been just looking up at the saturated pressure values. Now we calculated the vapor fraction indirectly based on the V value that we obtained using the polytropic process. Now that we know the process, from there we calculated V2 and we use the final pressure to determine the value of vapor fraction, from which we calculated the final internal energy. I hope this is clear. Yeah, I guess there are no questions, so we move on to the next problem. Now here, it's actually a reverse problem where you are asked to find the dryness fraction. So there is something called throttling here, so which we will discuss later also. So what we'll see here is, say initially your steam is at a certain pressure of 19 bar and it is throttled to 1 bar, and the temperature after throttling is found to be 150 Celsius. Calculate the initial dryness fraction of the steam. So what do I mean by throttling? So throttling is a process where you can assume it's an isenthalpic process. So you have H1 equal to H2. So what are the values that I know here? So initial pressure is given. Final pressure is given, and final temperature is also given. So all you are asked to find is find the initial dryness fraction of the steam. So if I can calculate H2 here, H1 is known to be equal to H2. So once I know the pressure and enthalpy, I can back calculate the value of dryness fraction from there. Okay, so how do I calculate H2? First look up the value of 1 bar and 150 Celsius. We know clearly that 1 bar is atmospheric pressure, but 1 bar, what is a saturated temperature for steam? Like saturated temperature at 1 bar pressure will be close to 100 degrees Celsius. So this is 150, which means you have to look up in the steam superheated steam tables. We'll just directly go over there. So again here, this is 1 bar pressure, and then you need to know the value at 150 Celsius, which is not directly given. So you need to do a linear interpolation between these two values, and we are trying to find the enthalpy. So I'll just take a highlight these enthalpy values. And you need to find it 150 Celsius. What is the value you're getting? Now that we have, we know what is H2 and we know that is equal to H1, since that is what we define a throttling process to be. Now our next part is to identify this. Identify the dryness fraction from these two values. So, so first of all, are we in the superheated region or are we in the dome? How do we determine that? So we know the pressure to be 19 bar. So if you look up the steam table at 19 bar pressure, at 19 bar it is going to be somewhere between these two values. So if you look up the enthalpy values, so this is internal energy and this is enthalpy values. The saturated vapor enthalpies. In our case, we obtained a value of around, this is at 15 and 20 and we need it at 19 bar. So 19 bar will be somewhere between these two values. And the value of enthalpy that we got from the isenthalpic process is 6.3. So this value is actually less than the value that you will obtain here at 19 Celsius. So sorry, at 19 bar. So at 19 bar, if you do the linear combinations, you will get a value of since it is less than this, you are still in the dome and you could be able to calculate dryness fraction. If for suppose if you have when you done this calculation and this H is actually greater than 2798.04, it means you are in the superheated region and your dryness fraction will be equal to 1. In the present scenario, since it is less than 1, which means you are inside the dome, so it will be somewhere between 0 and 1. So what is the other value? So we know the value of for this. So if you just calculate the value of HF as well. So now that I know the values of Hg and Hf, I can directly calculate the vapor fraction here, or the dryness fraction here. But just to note that you always have to check whether the value of H that you calculated is less than or greater than the value of the saturated vapor enthalpy at that particular pressure. If it is greater than that, you just put the dryness fraction to be 1. Okay, so now how do you calculate dryness fraction? You know the value of H1, you know the values of Hf and Hg. Are there any questions? Okay, let's move on to the next problem. Steam at a certain pressure and 100 degrees Celsius is to be condensed completely by a reversible constant pressure process. So the previous one, like we have discussed isothermal process. Now this is a constant pressure process. So we have discussed one on polytropic process. We have discussed an isothermal process. Now it's a constant pressure process. All you need to find is you want to condense steam, which is at 0.05 bar and 100 degrees Celsius. Use in a constant pressure process, which means in some open container or something, and you need to calculate the total amount of heat to be removed per kilogram of steam. How do I do that? So last week we have derived this, that in case of constant pressure process, just reiterating the fact that only in case of constant pressure process, the heat removed will be equal to, in this case, per kilogram of steam, so I'm removing the mass, so it will be H2 minus H1. And again reiterating it, that this particular heat will be equal to H2 minus H1 only in case of a constant pressure process, not for every processes. So how do I do that? So how do I calculate the initial and final states? Or if you were to put it on the PV plot, let's say this is my 100 Celsius line. This is some other temperature. This is basically this T2. This is T1. So we are at this particular point 1. and we are isothermally cooling till it is condensed completely. So by condensation, we mean most all of it is converted to liquid phase. So you move from here till this point, and then you also move till this point. So this is your final state. How do I calculate the final enthalpy at the final state? So we know the final pressure. So if you look at the saturated steam table and take the value of the saturated liquid enthalpy, that will be equal to H2. So this is basically HF at state 2. So again, you look up the steam table. So you have this and this. You just have to take a average value. So the saturated liquid enthalpy is this values. So you have just taken average value of them. And again, state 1 is in supersaturated region. So all I have to do is check the superheated steam tables. So let's just assume that this is close to 0.05 bar, which is the pressure that is given. So we'll directly take the value from there. And the temperature is 100 degrees Celsius, which is midway between both of this. So you just take average of this. This is the enthalpy that you would be considering. So now I have H1 and H2. I can directly calculate Q. Just as expected, this value is negative because heat is removed from the system. We are halfway through the class. So are there any questions? I guess there are no questions. So we move on to the next problem. As you see the pattern that all of these questions will deal more or less with, you just identify the initial state, final state, and then you calculate delta U based on the difference between them. The main step is how do you calculate the properties. So up until now we have been using steam tables. So you just look up the table, take some linear interpolation and get the value appropriately. But there are some there are some standards existing that from deciding how to take these values. For example, if you want to uh, code it in a computer, how do you do that and things like that. So let me know if some of you are interested in it, and we might maybe discuss that in some of the upcoming lectures. Maybe in next session, next week or next to next week, we can discuss how to actually code it and see. It's not part of the course, so only if you're interested, let me know. So we'll have around a 30 minutes discussion during one of these sessions if you're interested. Okay, so coming back here, so we have steam at 10 bar pressure and 250 Celsius. It is expanding until the final pressure becomes 2.75 bar. The dryness fraction of the steam at the end of expansion is 0.95. Determine delta U. Again, see, as you see, this keeps coming up. All you need to do is determine the properties at the appropriate states. It would be helpful to see this on a PV plot or a TH plot or some other plot so that you can visualize what is happening inside the process. So again, just to we have P1 initial as 10 bar. Yes, it is expanding till final pressure of, say if I want to plot it on a PV plot. So the initial temperature is 250 Celsius. So which region of the graph are we in? So how do we know that? Again, we look up the steam table. So one, we do not have the properties at 2.75 bar. So we were required to find U. So we know the dryness fraction. So we'll be using these values. First do a linear interpolation to find the value of UF and UG, and then you use the weight fraction, vapor fraction to calculate the value of U. The other one is the 10 bar pressure. So if you look at the value of 10 bar pressure, the saturated temperature is 179, while the current temperature is given to be 250 Celsius. We want it at 250 Celsius, so which means you are in the superheated region. So we look up the superheated steam tables at 10 bar pressure, and we know the temperature to be 250, so somewhere between these two, and we are asked to find the U value. So the temperature is given to be 250, so between this and this. I hope you are solving along with me so that you get to practice the problems as well. Now coming to the second state, as we have just discussed, you need to determine the appropriate values from the saturated steam tables. So now where to look? So these are the values here. So from this, you first calculate the corresponding values at 2.75 bar, which is actually the mean value of this. So UF will be, now we know the dryness fraction to be 0.95, or maybe I'll write it up there. Now that we know both U2 and U1, you can directly calculate delta U from there. And just to kind of reiterate here, so initially you were given some state. So this is my initial state. You are at some 250 degrees Celsius. So this is some 250 Celsius and 10 bar pressure. And finally, you are at somewhere inside the dome here. So all you know that this gas expanded from some initial state to some final state, and you do not know how it expanded, like whether it expanded in a constant pressure process or some polytropic process, isothermal process, adiabatic process. We just don't know which process it went through. All we know is it somehow moved from state 1 to state 2, and we know the properties of at state 1 and state 2, and since we know that, we can directly calculate u delta u from there. We do not require any other information to calculate this. That is what we meant by state function, which we have been reiterating every week as well. Okay, are there any questions in this? I guess there are no questions. So we move on to the next problem. So calculate the quantity of heat required to form 2.5 kg of dry steam at 11 bar from water at 20 degrees Celsius. Also determine the amount of heat removed at constant pressure to cause the steam to become 0.95 dry. Calculate the specific volume at each of the respective conditions. So state 1, we have water at 20 degrees Celsius. So let's say it's saturated liquid at 20 degrees Celsius. 20 degrees Celsius. And then what we are doing is so why I'm saying that the pressure is constant here. So you're moving from the saturated liquid to the saturated vapor phase. So if you see it in the curve, it will be both a constant pressure as well as a constant temperature process. That's why both the initial and final pressures are the same. So if you're moving inside the dome from saturated liquid to saturated vapor, so this is a constant pressure line. It is also a constant temperature line. So this is my temperature line. Inside the dome, the temperature is also constant as well as the pressure is constant. It's both an isobaric as well as an isothermal process. However, just as we discussed before, even though it is an isothermal process, delta U is not zero because phase change is happening inside. Now coming back to the problem, so how do I calculate this? This is what in the steam tables is referred to as HFG. So all you need to do is look up the value at 20 Celsius and 11 bar pressure. Now this can be done in two ways. So we have two different steam tables. You can either look up a temperature steam table or a pressure steam table. If you are looking up the pressure steam table, then you need to look up the value at 11 bar pressure. So you need to look up a value somewhere between this and this. And HFG, like as I was saying, this is the evaporation one. So this is the HFG that I was referring to. So it's basically like your latent heat. Alternatively, you can also use the temperature table. So in the temperature table, we will be given temperature. So the temperature is 20 degrees Celsius. then your pressure is a little different. We'll stick to the pressure. Yes. So now if you see at 10 bar pressure, the saturation temperature is 179.9, but the temperature in our case is given to be 20 degrees Celsius, which means we are in the subcooled region initially. So from subcooled region, you have to move up to the saturated liquid, and from saturated liquid, you have to move up to the saturated vapor phase. So So this is the compressed liquid, which is subcooled liquid phase. Inside subcooled liquid phase, we can look up the values. You can see the value at 20 degrees Celsius. So let's say, okay, let's use the value of 25 bar. Uh, Otherwise, you have to just do some interpolation. I'm just changing the values here so that you don't have to do the interpolation. We'll directly use the values from there. At 20 degrees Celsius and 25 bar, you have the value of H to be 86.3. So what are we doing? So we'll use these values from 86.3. So you're initially in the subcooled phase, somewhere here. So this is 1, this call is 2, and this call is 3. H1 from the compressed liquid table, we got it to be 86.3. And H3 minus H2 is basically HFG that I was referring to. And this we need to look up at the values of 25 bar. So at 25 bar, we can calculate the value, we can look up the value. So this is the HFG value. Again we were saying that it is inside the dome, or even in this process, throughout the process your pressure is kept constant. So since it is a constant pressure process, you can calculate the amount of heat to be there. H3 minus H1. We can look up the value of H2 directly from the table. We can just take the value. That is for the first part. Now, for suppose if you want to remove certain heat, so you are in the saturated vapor phase, that is at point 3. So what you want to do is you again want to remove it such that you would reach a stage where you have somewhere here 4. So you're moving from 1 to 2, 2 to 3, and 3 to 4. Now you are at stage 4. At stage 4, you want to have a dryness fraction of 0.95. This is again straightforward. So how do I know H4? It is a dryness fraction of 0.95. So it is 1 times HF, or since we know HFG directly, I can write it as your dryness fraction times enthalpy of fusion. So that will give you, this is equivalent to saying 1 minus HFG is HG minus HF. So both are equivalent. Now we have H4, so we can directly calculate the Q as final minus initial state H4 minus H3. So again, the next part asks you to find specific volume at each of the respective conditions, which is again straightforward. So you directly have to look up the steam tables and then get the values directly from there. So for example, we'll just go through one by one. So at state 1, which is in the subcooled liquid phase, in the subcooled liquid phase, you directly get the value of V here. So this is the volume here, which is very low. Like as we expect in the subcooled phase, the specific volume is very low. This is 1 into 10 power minus 3. Similarly, now you need to determine the values at the other two phases, which is Vf, Vg, and at the dryness fraction, which are again straightforward. We have been doing this linear weightage from long time, so I'm just skipping that part. Hope there are no questions in that. Are there any questions in that? If there are no questions, I'll skip that part and we'll move on to the next problem. So how do you calculate specific volume? For state 1, you need to look up the subcooled one. For state 2, you just need to look at Vf at 25 bar. For state 3, you need to look up Vg at 25 bar. State 4, you use V2 and V3, and from there you calculate the, basically it will be V2 times 1 minus, we know the fraction to be 0.95. Whatever you calculated stated, this will be V4. I hope there are no problems in it. You can look up the steam values and then substitute them back here to get your answers. Is there any questions? Okay, we'll move on to the next problem. This is actually an interesting one, like we have been discussing previously also. The change in internal energy that you consider in case of an ideal gas versus in case of these real gases like steam might be a little different. We just want to highlight how much this difference is actually in the case of steam. When you assume the ideal gas law that we know, the isothermal case that we usually use, that is PV equal to constant, and then compare it with the steam tables that we are using right now, and then see what is the difference between these and try to understand what is actually causing the difference. If you see in this case, you have a certain amount of a dry and saturated steam at 1.5 bar. It is occupying an initial volume of 2.32 cubic meters. It is compressed until the volume is halved. And when it says the volume is halved, the mass of the system remains the same. So your specific volume will also be halved. Part 1 asks you it's an isothermal compression. Part 2 says it goes according to the law of PV equal to constant. Determine the final condition of the steam in each case. Also determine the heat ejected during the isothermal compression process. First, we'll solve the first case. So how do I determine the final condition of the steam? So initial condition is given, the pressure is 1.5 bar. Just to not confuse with the specific volume and total volume, I'm just putting this extra horizontal line. The initial volume is 2.32, and initially it is in the saturated phase, so I can calculate the specific volume directly from the steam tables. So it is at 1.5 bar, and it is in dry saturated region, so you have to look up this value from here, 1.159. So from both of this, we can calculate the mass of system, that is approximately 2 kilogram. So what do you have to do now? So in case of an isothermal process, what is the final state? If your volume is halved, so V2 is halved, the mass of the system is remaining constant, so your V2 will also be halved. And isothermal, so T2 equals to T1, which is equal to the initial saturated value. So at 1.5 bar, the saturated temperature was So all I need to find now is what is the value, what is the final state. So you know the initial state to be 1.5 bar, sorry, you know the temperature to be 1.4, and then you also know the specific volume to be 0.5795. So are these two values sufficient to determine the final state, or do I need something else? So if you are inside the vapor dome, all you require to know is, so if you look at the PV plot or the Morris diagram, so you have P and V. So initially you're on the saturated region at certain pressure of 1.5 bar. So this is 1.5 bar. Now you are going isothermal, all you are doing is you are actually compressing it. So your specific volume is getting reduced. So you are moving in this direction. So if you happen to be within the dome, you're still inside, you're still at the same pressure. But it can also happen that you might end up at something stays like this. So you can either be here. So this is also isothermal process because temperature is constant. You can also be here. You can also be here somewhere. So how do I know which state I was in? So if you know the temperature alone, which I already know, and you know the specific volume, so you should be able to fix the final state. So with these two properties, you like once you determine the value of V2 as 0.5795, once you put that here, you will know whether you are this region or in the saturated liquid or in the subcooled region. So which state are we in? So for that we need to look up the steam table again, but instead of the pressure table, we'll be looking up the temperature tables. So at around 111, so I'll take this value as 110. So at 110, my specific volume is 1.21, and this is 1.0516 into 10 to the minus 3, while the value that we got is around 0.5795. So this is less than, or I'll just write Vg, which is somewhere between Vg and Vf. So which means I'm still inside the dome. So I'm in the two-phase region. So I'm somewhere in the region like this. So this is my initial state 1. I'm somewhere in the region. So I can calculate the dryness fractions. Like for example, I was so now that you know that this is inside the dome, you are moving along this line. So isothermal process is equal to your isobaric process. How do you determine your heat transfer? So heat will be basically enthalpy difference, that is H2 minus H1. And H1 I already know. Your H2 will be depending on your vapor fraction, HF plus, and initially you're in the vapor phase, so this will be He. So how do you calculate the vapor fraction? In this case, like Pf is around 10 to the minus 3, so you can neglect that as well. So this will be approximately just using some approximations, but then you can also calculate them directly. Like I said before, you can also directly take the value from the HFG from this. That is a enthalpy value. We have already calculated the total mass, so the net heat transfer will be this is using the steam tables. Now, suppose if you stick to the same original law that we already had before, which means, for example, if this particular steam is following an ideal, if it obeys ideal gas law, then we have PV equal to constant. So how do I calculate the final specific volume? So I know initial pressure, I know my initial volume. This is what we will have to be using. The volume is halved, which means pressure should be double. So now you ended up at a different state, which is a 3 bar pressure. Instead of 1.5 bar, now you are at different pressure. At 3 bar pressure with a specific volume of 0.5795. So if we look that up, at 3 bar pressure, your saturated vapor phase is 0.6058, which is less than your 0.51. If you were to look at the enthalpy value, these are the enthalpy value. So again, we follow the same process as we have done before. So you know P2, and you calculated V2 to be 0.6, sorry, your V2 is already known to be 0.5795. So your vapor fraction is approximately 0.5795 divided by the specific volume at the vapor phase at 3 bar pressure, so which is 0.6058. and you know the HFG value. You can also directly take the HFG value from the table. That is around 2160.8. HF is around 561.47. So we have the vapor fraction, so we can calculate the final state. And we can also calculate the initial state, which I think we didn't calculate previously. So you can calculate H1 as well. You know the previous dry fraction to be 0.48, and it is at a pressure of 1.5 bar. So you can see how different the values are between using PV equal to constant versus the one that we have obtained. Sorry. So I think I just made a mistake. Yeah, in case of an isothermal process where PV equal to constant, you cannot directly use Q equal to H2 minus H1 because just as we said that equation has to be used only for the case of a constant pressure process. So in this case, we need to determine the work done, and from there we need to calculate delta U. So what is the work done in case of an isothermal process? V2 by V1. We know the initial pressure. We know the initial specific volume, and we know that the volume is half. Now we need to calculate delta U. U1 is the saturated value at this particular point, and U2, now at this particular stage, we are at 3 bar pressure and somewhere inside the dome here. So I'm just calling it 2 prime or something. So 2 prime is for the second case. Actually, 2 prime is something we got vapor fraction around 0.95. So this will actually be close to somewhere here. We'll just take the values directly. So we need two values, one at initially at 1.5 bar, the other one at 3 bar. At 1.5 bar, we need to take the saturated value, which is this. And at 3 bar, we need to take the considered vapor fraction and then take the corresponding value of these two. So U2 prime is in U1. If you take the value directly from there, now that we have both Q as well as U, we can delta U and W. We can calculate Q to be W plus delta U and multiply those values with the mass that we have calculated already. So that gives me so you can see how up these values are. First, your final state itself is different by assuming P1 V1 equal to P2 V2, which is not true in case of real gas because we do PV equal to constant is true because when you use ideal gas law, we have PV equal to MRT or PV equal to RT, and then in isothermal process, since this is constant, we have PV equal to constant. But in the present scenario, when you consider water which doesn't obey this ideal gas law, even when temperature is constant, you cannot assume PV equal to constant. So just like you see when we use the steam tables here, we ended up being the process, though it was an isothermal process, because of the phase change process, we ended up being in a constant pressure region instead of moving to a higher pressure. So this problem is just to reiterate the fact that whenever you have these two phase things, look up the tables. Don't use ideal gas law. You're allowed to use ideal gas law only in this region, in the superheated region, not inside the dome. That's it. That's the main conclusion that I would like you to make from this particular problem. I think there was some mistake that I have done when I was solving the first couple of problems, where I was looking up the values of enthalpy. The process still remains the same. The only thing that is going to be different here is, sorry, not this one. Yeah, I think I made some error while calculating the value of enthalpy. So I've taken, instead of considering the vapor, I would have considered the fusion. So just look for those values. You should be able to calculate it yourself and let me know if something goes wrong, if something is not clear with respect to the process. Okay, moving on to the next problem. We have a closed vessel of certain volume and that contains steam at 8 bar and 200 degrees Celsius. Determine the mass of the steam in the vessel. First one is straightforward. So how do I do that? I need to calculate the initial specific volume. So I know pressure, I know my temperature. From both of this, all I need to know is calculate V1. And once I get V1, capital V, the total volume is given to be 0.3 meter cube. So mass of the steam is going to be V1 by V1. So this is straightforward. How do we calculate? So at 8 bar and 200 degrees Celsius, I'll just look up the steam tables. So it will be in 8 bar, saturated temperature is 170.4, which means you have to look up the superheated tables. So I'll just approximate it to be value around 7 bar and 200 degrees Celsius. Your VA is around 0.3. So I'll just use a value of 0.3. So the mass is around 1 kilogram. Second part, the vessel is cooled till the steam becomes just dry and saturated. So basically you are in the superheated region and now you are moving to the saturated vapor state. What will be the pressure of the steam in the vessel at this stage? So it is a constant volume process. So and the mass, the vessel is actually a closed vessel, so the mass is also remaining constant. So your specific volume also remains constant. So if you were to plot it, on the PV diagram, so initially you are at 8 bar pressure. Let's say you are at a very high point. So at this stage, give this more little. So we're at this phase, and we are saying that you are moving in a constant volume. You are cooling it in a constant volume process. So you are moving from here to saturated vapor region. So somewhere here. So this is the process. And you are asked to find what will be the pressure of the steam in the vessel at this stage. So all you need to do is find the pressure at this stage. So how do you do that? You know the specific volume at this state, and you know it is going to be in a saturated vapor phase. So all you need to know is when you are looking at the steam table, find the value of pressure, find P from pressure table, where Vg is close to 0.3 meter cube per kg. That will be your final pressure. So how will I do that? I'll just go to the steam tables. So it is in the saturated region. So you need to know a value of around 0.3, which is close to 6 bar pressure. This is around 0.3157. So I'll just go with this value. So the final pressure is 6 bar. Okay, I think this is clear. Now what is saying is the vessel is further cooled. So even from here, you are further cooling it down. You are still going to a new stage. So your pressure will further be reduced. Now this is your state 3. Till the temperature drops to 158.85 Celsius. So at third part, you are saying that the final temperature is 158.85 Celsius. And you will be inside the dome. All you need to know is to determine the pressure and condition of the steam. So you know the temperature. So how do I know the final pressure? So you look up in the saturated temperature region. So you look up the pressure table and see if you're just write it down. So find P from pressure table, where your saturated temperature is equal to T3. So if you look up the saturated temperature table, you need a value of around close to 158.85. That is again close to 6 bar. So you're still within the same pressure. So and you know the specific volume is equal to it. So the dryness fraction is equal to 1. So it happens that this is at the same pressure, that is 6 bar. So 2 is equal to 3. Okay. Are there any questions? Yeah, the only difference from the problems that we have solved up until now and this one is till now we have solved, like we have covered most of the problems that have, we covered the polytropic process, we covered adiabatic process, we covered an isothermal process, we covered an isobaric process, and this is the only one where we have an isoporic process, that is a constant volume process. So if suppose I were to ask you to calculate the work done in the process from say 1 to 2, how would you go about that? So maybe we can quickly do it if you can see. So at the initial state, you know the enthalpy, sorry. So from 1 to 2, your volume is constant. So what is your work done? Is 0 because it's a constant volume process. U12 can be calculated as U2 minus U1, and from there you can directly calculate Q to be U2 minus U1. Basically, it's a constant volume process, so Q will be equal to delta. I hope this is clear. So we'll move on to the last problem. This is again a very straightforward problem. So 1 kilogram of water at 30 degrees Celsius and 1 bar is heated at a constant pressure until it becomes saturated vapor. Determine the change in volume and internal energy during the process. The only difference in this from the previous problems here lies in the determining the state of it. So at 1 bar pressure, the saturated temperature is 100 degrees Celsius, but it says that your initial temperature is 30 Celsius, which means you are in the subcooled region. So mass is 1 kilogram, so I'm just ignoring that. And until it becomes saturated vapor. So if you were to plot again on the PV1, so this is your 100 degrees Celsius and this is your 30 degrees Celsius. So you have to heat from here. This is state 1. This is your saturated liquid. This is your saturated vapor. So all you need to do is look up subcool tables at 30 degrees Celsius and 1 bar. Get H1, and then at 1 bar you can calculate H2 and H3. So usually in these problems, like from an engineering point of view, H1 is very less compared to H3 minus H2, or let me put it in slightly differently. Maybe I should say H2 minus H1 is actually very much less than H3 minus H2. So you can directly calculate the change in internal energy, or it's the same goes with your enthalpy and internal energy. So you can directly calculate U3 minus U10, that will be very close to the value that you get from. How do we calculate the change in volume? You know, again, V1 is very less compared to V2, which is very much less compared to V3. So the final change in volume is V3. I'm neglecting these two components. So it's V3 minus V1, but then V1 is small and mass is 1. So that will be equal to delta V. Are there any questions in this? Yes, there are no questions. Yeah, I hope it is clear. There are no questions. So thank you for joining. We'll meet again next week at the same time, 5 o'clock on Saturday. Thank you. Thank you all.